Hi everyone, welcome to my channel. In this video, we will see some solved problems on Norton's theorem for DC circuits. The procedure for Norton's theorem is explained in the previous video. The link is there in the description, so please go through it. First problem is find the current through the 10 ohm resistor by Norton's theorem. So from the given figure, it is a bridge circuit and he asked to find the 10 ohm resistor. So we have to treat the 10 ohm resistor as a load resistance, and according to Norton's theorem, to find Norton's current, we have to remove this load resistance by a short circuit. So and we have to redraw the circuit as shown in this figure. And again, the simplified circuit is shown in the figure. So from the figure, ISC, nothing but short circuit current, it is nothing but the current supplied from the battery itself. Therefore, after simplifying the series and parallel branches, so we are finding the equivalent resistance, that is 9.3 ohms. So then after, the short circuit current is given by the 50 by R equivalent, therefore that is 5.37 amps. So this is the short circuit current. We know that the short circuit current is also called as Norton's current. So therefore IN is equal to 5.37 amps. Now we have to find out the Norton's resistance. So to find the Norton's resistance, we have two steps. The first step is we have to remove the load resistance to form an open circuit. Now second step is we have to deactivate all the sources in the given network, and the third step is we have to calculate the Norton's resistance from the open circuit side. So upon removing the load resistance and deactivating the sources, the equivalent circuit is shown in this figure. So from this figure, we have to find out the Norton resistance across the two terminals A and B. Now again redrawing the circuit here. So this is the redrawing circuit, so between the terminals A and B. So now if you observe, this is in the delta shape, A, C, D, it is in the form of a delta. So converting this delta into star, so this is the shape we are getting. So we have to calculate the star connected values. So by using the star to delta and delta to star conversion, so that is also covered in the previous videos. So please go through the link, and we by using the delta to star conversion, we can calculate the delta values as 2 ohms, 1.33 ohms and 1.6 ohms. After converting this delta to star, again this incorporating this delta shape in the given network, that is a converted network. So this is the equivalent circuit we are getting for calculation of our Norton's resistance. Therefore, from the circuit, so that these two resistances are in series and these two are in series, and again these two are in parallel. So this entire combination is series with 2 ohms. Therefore, the resistance between A and B terminals is 4.98 ohms. This resistance is also called as Norton's resistance, that is 4.98 ohms. Upon calculations of this Norton's current and Norton's resistance, we have to draw the equivalent circuit by connecting the Norton's current with a parallel resistance, that is Norton resistance. So this is the Norton's equivalent circuit connected to a load resistance, that is he asked the current in the 10 ohm resistance. Therefore 10 ohm resistance is the load. So therefore by using current division rule, we can calculate the current in the 10 ohm resistor by using the formula IL is equal to IN into Rn by Rn plus RL, that is opposite resistance by total resistance, that is multiplied with the total current, that is Norton's current here. Therefore the load current is calculated as 1.785 amperes. Next, second problem. So find the current through the 20 ohm resistor by using Norton's theorem. So here also is a 20 ohm resistor here. So to find the Norton's current, we have to remove or replace this 20 ohm resistor with a short circuit, and we have to redraw the circuit. And upon replacing with a short circuit, there are two loops in the given network. So here the two currents I1 and I2 are flowing in the two loops. Therefore the ISC, that is the short circuit current, is nothing but the summation of the two currents. Therefore ISC is equal to I1 plus I2, where I1 is nothing but where I1 is the current in the first loop. Therefore it is calculated as 75 by sum of the two resistances 10 plus 10 20, therefore 3.75 amperes. And I2 is the current in the second loop. Therefore I2 is equal to 25 by 25 plus 5 30, therefore it is 0.83. Since these two currents are in the same direction, therefore ISC is nothing but summation of the two currents. Therefore, ISC is nothing but 4.58. We know that short circuit current is also called as Norton's current. Therefore, IN is equal to 4.58 amperes. Then after we have to calculate the Norton resistance. To calculate the Norton resistance, we have to remove this 20 ohm resistor, and then we have to deactivate the sources in the given network. So from the given network, we have two voltage sources are there. We have to make these two sources are a short circuit, and then the equivalent circuit is shown in this figure here. Upon removing the load resistance, that is 20 ohm resistance, and deactivating the sources, this is the equivalent circuit. So from this equivalent circuit, so we have to calculate the Norton resistance Rn. So upon observing the circuit, 10 plus 10, these two are in series, and 25 and 5, these two also in series. So with respect to the Rn, so these two are in parallel. Therefore, Rn value can be calculated as 12 ohm. Therefore, the Norton's equivalent circuit is shown in the figure by connecting the Norton's current source with the parallel resistance. Next, it is connected with the load impedance 20 ohms. Therefore, IL, nothing but load current, can be calculated as IN into Rn by Rn plus 20. There is a parallel current division rule. So, IL value can be calculated as 1.72 amperes. Next, third problem. So, find the Norton's equivalent circuit at the terminals X and Y. So from the given term, he just asked only the Norton's equivalent circuit with respect to terminals X and Y. So Norton's equivalent circuit means it is consisting of Norton's current source and with parallel with a Norton resistance. So that means we have to calculate only the Norton's current and Norton resistance. So first, to calculate the Norton's current, we have to short the two terminals X and Y, short the X and Y terminals, and we have to redraw the circuit as shown in the figure. Since there is a short circuit across 5 ohm resistor, therefore there is no current flowing in the 5 ohm resistor. Therefore, upon removing this 5 ohm, so now we have to calculate the current in the short circuit branch. So from the figure, if you observe here, apply KCL at this node, I0 plus is the current source is current dependent current source is there, that is whose magnitude is 2 into I0. Therefore 2I0 plus I0 is equal to ISC. Therefore ISC is equal to 3 times I0, where I0 is nothing but current from the battery itself. Therefore I0 is equal to 12 by 10. So that is 1.2 amperes. Therefore ISC, that is short circuit current, can be given as 3.6 amperes. This short circuit current is also called as Norton's current, that is 3.6 amperes. Upon calculation of Norton's current, we have to calculate the Norton resistance. To find the Norton resistance, we have to remove the load resistance, if any. Since in the problem there is no load resistance is given, he already given with open terminals X and Y. So then second step is we have to deactivate all the sources in the given network. So in the problem we have 12 volts independent source is there, that is voltage source. We have to short circuit this voltage source, and the equivalent circuit is shown in the figure. Now since when the dependent sources are there in the problem, so it is difficult to solve by normal method, that is with respect to open circuit we have to calculate the resistance value. So that we are using other method, that is we are calculating the open circuit voltage from the given network. So upon deactivating of the source, we are calculating the open circuit voltage. So by applying the KCL at the node X, so we are calculating the VDC value, and so from this voltage source generating a current IDC. So that if you observe the if you apply the KCL at this node, so here the current I0 is flowing in the opposite directions from the given network. Therefore I0 value is minus VDC by 10. That is here the voltage at the node X is nothing but VDC. So therefore the current I0 is given as a minus VDC by 10. Here the minus is because of the current which is opposite from the given network. That's why we are putting the minus sign there. I0 is equal to minus VDC by 10. So by applying the KCL normally, so we are getting this equation where I0 value is minus VDC by 10. Upon simplifying these two, we are getting the ratio VDC by IDC. So this VDC by IDC nothing but Norton resistance Rn value, that is 2 ohms, After calculations of Norton's current and Norton resistance, the equivalent circuit is shown in the figure, that is Norton's current with a parallel resistance, that is Norton resistance, as shown in the figure. Thank you.